Welcome back from our break. I'm Jim Bell. I'm one of the team leads for this study from Arizona State University. Planetary science, surfaces guy, asteroids, moon, Mars, you name it. This is definitely a lot of fun. Enjoyed the first talks this morning. We're going to continue our short course. And this presentation was put together by Kimberly Moore, research scientist Kimberly Moore, who could not be with us today. But we wanted to make sure we establish her credibility. PhD from Harvard, Earth and planetary scientist, working on the NASA Juno team, among other projects. She was 51 Peg B postdoc at Caltech, and she's still a co-I on the Juno mission. She's been involved in a number of concept studies related to interstellar objects through JPL Science Seminar Series and others. She's written white papers on this topic for the Decadal survey, et cetera. So certainly grateful to Kimmy for putting the presentation together. In Kimmy's place, one of our other co-leads, Benji Donitz, will be giving her presentation, your slides, and probably putting some of your own little flair on it, I would imagine, as well. Benji is a project systems engineer at JPL, who's been also involved in a number of mission studies related to small body exploration and other kinds of exploration. And I'll let you fill everybody in on some more of your background. So let's have Benji come up and give the presentation. Thank you.
Thank you, and sorry Kimmy can't be here, so I will do my best to present in her place. And I'll answer questions at the end. If there's any that we want to address to Kimmy, maybe we'll send her an email later and see if she's available to respond. I'll be presenting today on some of the importance, in addition to what Karen presented on, the importance of why we have to respond quickly to things like interstellar objects and long-period comets, and also a bit on planetary defense. I'll say things like JPL study said this is in a new frontiers or discovery or a small sat class. That's not meant to be any sort of cost commitment. So just the disclaimer here, so nobody mistakes this for a commitment on behalf of JPL or Caltech or NASA or anyone else. We'll talk about a few things today, about proposal timelines, about target detection, a few concepts for rapid response or architectures, as I'll often refer to them, and also challenges and an outlook to the future. Normally, when we plan a mission, we know where we're going. We've detected our target many years ago, usually, and then we design it or formulate a mission concept, build it or implement it, depending on the language that we use, and finally launch it and operate it and achieve great science and come back home and we're all ecstatic based on what we've done. We can think about Juno. As Jim mentioned, Kimmy worked on Juno. We discovered Juno, I don't know when. I'm sure somebody knows that fact. I'm guessing at some point in ancient Greece or something, but for a long time, we've known where Juno is. And if we ask some of the navigators here in the room, they could tell us extremely precisely where Juno is today, where it was 1,001 years ago, and where it will be for the next million years or so. We have excellent knowledge of the position of Juno over time. If we look at Juno was, I learned this just from this presentation, Juno was first proposed as a mission called Inside Jupiter, and that was back in the late 90s as part of a discovery mission. A discovery mission is about a $500 million class. It was a finalist, but wasn't ultimately selected. And then several years later, it was reproposed as part of a New Frontiers mission. I think it was New Frontiers 2 or 3, I can't recall exactly, one of the earlier New Frontiers mission. And in 2004, it was selected. As we talked about, we implemented it, we formulated it, we implemented it. And then in 2011, we launched. And then currently today, Juno is operating at Jupiter and accumulating extraordinary science. And this represents something like our normal mission life cycle. So let's take a step back. We could talk about these traditional planetary science missions that cost between $500 million and $1 billion or so. Every 2 to 5 years, we go through about a year-long process to go and select these missions. We propose them, we select them, And then it takes about 5 to 10 years from selection to launch. So we add that all up and we say, okay, maybe it's about 10 to 15 years, but a decade and a half to go from I'm going to propose my mission concept to I'm going to launch it. And that doesn't even necessarily take into account all the previous generations of missions that we often see. I have an idea to I'm going to launch it might be far longer than this decade time frame. But we could say a decade. A decade is about the time it takes to go from proposal to selection. Small set missions tend to be a bit more aggressive, a bit faster. There is some downsides to them too. And here, when I say small set, I'm mostly referring to the NASA Simplex. And today I'm talking mostly from the NASA perspective, but I'll touch a little bit. Kimi put some slides in here on ESA and JAXA, but I'm delighted to have representation from ESA and JAXA here too. So I'm excited to have these conversations and compare and contrast how different agencies do this. But I'm just going to talk about from the perspective that I have, which is NASA. So these NASA small sat missions in Planetary are simplex. They're called simplex missions. They originally were 55 million, and the Decadal recently recommended that we up that cost cap a little bit so we can achieve even more science in these smaller platforms. So I said about 55 to 100 million. I think the recommendation was closer to 85 or so. These are generally ride-alongs, meaning we don't have as much control authority or as much flexibility about where they go or when they launch. We are often more constrained to riding along with other larger missions. So as a result, for example, the Escapade mission, which was a small set mission, it was supposed to ride along with Psyche. There was delay in Psyche, and now the Escapade mission is figuring out its launch situation. So it hitched its horse to Psyche, and unfortunately that didn't go as originally planned. So that's an example of how rideshare could be a potential risk. In ESA and also in JAXA, we can see sort of a similar time span. So about, if we look at Rosetta, about 10, 11 years from when the mission was approved to when it launched. And in JAXA, Hayabusa, we have, I guess, a shorter time span from approval to launch, but 7 years from when initial studies took place through when it launched. So we're still talking about that on order of a decade, maybe a little bit faster, but still comparable. And also a note here that there's a lot of collaboration between all these different agencies, either instrumentation or contributed instruments, things of that nature. Rapid response is we throw this whole idea out the window. We don't, unlike Jupiter, we can't say for certain, we want to go to this object and we know where it's been, we know where it will be, and most importantly, we know where it is today and when my spacecraft eventually arrives. This detection becomes a big question mark. And we're looking now for newly detected objects. I also talk a lot about missed opportunities. I always like to refer to these three, mainly because these are the three that I've seen in my relatively short career looking at these objects. But I'll refer to 2 interstellar objects and 1 long period comet, 1 extraordinary long period comet that would be awesome to go discover. The first is Oumuamua. We heard about Oumuamua and Borisov. Oumuamua we detected on its way out of the solar system, just past perihelion. Borisov we detected just prior. And then comet C2017K2, or I'll call it K2 mostly, we had 5 years, a long time, to go and observe this target. And we could see this is it. I think this was out near Neptune or something like that, this image that was taken by Hubble. And it's massive, and it has all these great volatiles that Karen was talking about. And if only we could go and observe this up close and characterize this long period comet that's been on its way for millennia or millions of years to visit us. And interestingly enough, we're just shy of perihelion. So hopefully in a couple of months, we'll be able to look to the night sky and see a beautiful comet. And we might wish, if only we could have gone to visit it up close. So let's talk about missed opportunities. And then NEOs, we also know NEOs there are no missed opportunities, thankfully, but we could think about NEOs as well as rapid response. We just discovered something for the first time and we have to act now. We may ask ourselves a question as well, how far in advance can we actually go and detect these objects? And I'll skim over this period, these couple of slides because we talked to them a little bit before, and I think Joe's going to give a really great talk on this tomorrow as well. So just to refresh everybody, we have Pan-STARRS, which is doing all-sky surveys today, and Vera-C Rubin, which will come online, we hope, any day now. Next year is when we expect to have the actual science beginning, and that's going to be able to detect much dimmer objects. And recall in magnitude, we want lower numbers. Lower is brighter. So if we can detect higher magnitude, that means we can detect dimmer objects. One challenge is that also we have a huge variety of brightness here. Some of these comets, these active comets like Borisov, that's pictured here on your left, is this big, grand comet that's so bright in the night sky, and therefore we could probably detect it much sooner, as opposed to these asteroid-like interstellar objects or some NEOs that might be not active or not apparently active, be dimmer and have a lower apparent albedo. And that might cause us to detect them much, much, much later, and maybe also pose a challenge for navigation. Because that's another element here, is here we're talking about the on-the-ground detection, but at some point, hopefully we'll actually go and fly by these targets. And navigating to these much dimmer objects is also much more challenging than navigating to this big, bright, active body that what we might be able to detect using our onboard imagers far, far, far farther out than these dim and small asteroids. We saw this plot. The detection over time has increased. We see C 2017 K2 up there. I wish we could have gone to see it. We'll talk a bit about that later on. And as NEO Surveyor comes online and Vera-C Rubin, we expect this plot just to increase even further as we go along. So for LPCs, notionally, we might think that we can detect several per year, a couple years out before perihelion. We talked about K2. K2 would detect about 5 years out before perihelion. And hopefully, with these other big, great comets, as they're sometimes referred, we can detect them a couple years out. ISOs might be much more challenging. Of the two that we saw, one we detected -1 months out from perihelion, and the other one just a short 3 months out from perihelion. But as I think it's Darrell's group wrote a paper that we refer to here, the Hoover paper, that we think that we'll be able to detect on order of 1 to 2 ISOs per year once the Vera-C Rubin Observatory comes online. We also saw this plot. We're observing more and more and more NEOs as time goes on. So detection really becomes this problem in our standard mission timeline, where these big project milestones still all have to occur, but when they have to occur is now up for debate. We no longer have to follow this traditional linear path. So the solution is rapid response, what we're all here this week to address. And rather than us having this linear progression from detection to launch and operations, these become more puzzle pieces. And maybe we have the opportunity to ask ourselves, where should each of these things go? In what order should we complete these series of activities or these milestones in order to have our optimal mission lifecycle? And hopefully this week, we're going to go and devise a couple of these different architectures. And here I'll go through 3 and talk about 2 in detail. And one of them, Grant Jones will talk about next, which is Comet Interceptor. So number 1, we could say, we're going to build this thing and store it on the ground. We're going to design it, we're going to implement it, and we're going to somehow stick it in cold storage until the moment we detect our favorite object. And there's also a whole thing that I hope we address, which is, how do we actually decide that? How do we decide we do want to go and we spent all this money to build this thing and stick it in storage for years? How do we decide that this object is worthwhile? Especially when sometimes we have a really compressed timeline, because maybe there's 6 months from detection until when we'd have to launch. What activities do we have to complete in those 6 months to decide, yes, we want to go expend our resources, we want to go visit this particular object? One example of this is the bridge concept. This was the JPL Planetary Science Summer Seminar concept that Kimi led in 2019. And the idea was to build a spacecraft as well as an autonomous impactor. Karen mentioned how sometimes what we see on the surface isn't necessarily representative of what's on the inside. So maybe we want an impactor to reveal any fresh surface, remove the effects of space weathering and things like that. to get a better idea of what is this target or get some new science objectives. We build the spacecraft, stick it in ground storage until we detect a target. And for this concept, the science objectives were to reveal the chemical and isotopic composition, including organics and surface morphology. And the payload consisted of a camera, that impactor, as well as near IR, mid IR, and UV spectrometers. Here, this is why this disclaimer is in place. The JPL formulation team, concurrent design team, Team X, said that this would be around a Discovery or New Frontiers class. There's a really awesome paper that details this bridge concept, and I will drop that paper in our Google Drive so people can refer to it at any point. The second one, and this is the one that I'm going to skip over because we'll hear about it more in just a few minutes, an actual implementation of this, what I think it's the first rapid response mission of its kind, is we design it, we build it, we launch a spacecraft into a parking orbit, and then when we detect an object, then we go and we launch from our parking orbit. And I'm going to skip over this next slide. And then a third thing might be maybe we don't build anything. Maybe we want our spacecraft to be as bespoke as possible. We want to optimize either our engineering subsystems, like we want to have the right amount of delta V. We don't want to be too big or too small. Maybe we want to optimize our science payload suite, that we want to have this, we're interested in this spectra, not that spectra, based on something that we've uncovered with remote observation. So in this concept, we still want to design it. We still want to have plans in place. And design is the whole project, not just the spacecraft. But how do we launch it? How do we engage all of our partners? How do we set up the ground system, as some people mentioned in that survey that we were all filling out in the weeks until now? So how do we design this whole project so at the moment we detect something, we could extremely rapidly build it or implement it and then launch and operate? And one example of that is a concept we looked at JPL a few years back. We called it Xenia. And that was two twin small sats that would go and look at comet K2. You can kind of see a common thread. I happen to like that comet. And then the science was to go and constrain the temperature of the protoplanetary disk, inform planetary and solar system formation, and also observe some nucleus jet activity. And here we had an extremely tiny UV spectrometer as well as a high resolution camera. We thought this was about consistent with the increased simplex cost cap. But what's really constraining here is that no dedicated launch or no PI procured launch. That becomes a real challenge. It was a real challenge in this mission and would be a real challenge for other missions, because we just got to get lucky. We got to get lucky that we know we have to launch to the right place at the right time, and somehow that has to align perfectly with where another larger spacecraft is also going, just so happens to be the right place at the right time. So that can be a real challenge. So even if we had the money, we'd need the launch vehicle as well. So how can we enable this ISO mission concept the next decade? I'll get into a couple of challenges and recommendations that several of us, led by Kimmy, put forth in the Decadal survey, and what the result of that was, and then we'll conclude it. So one of maybe even the larger challenges is programmatic here. We think in many ways we could build it. Technically, we could build a spacecraft of this, but programmatics becomes a real challenge. We have to, we know that we're only discovering these shortly prior to their perihelion or to a required launch date. That's why we need rapid response. But these opportunities, the NASA science opportunities, AOs, NASA opportunity only come out every couple of years, every 2 to 5 years is what we said before. And that's probably about right. Maybe it's on average, 2 to 5 years. So we want these rapid response architectures, but how do we negotiate those two things, where we want to build something on demand, but the AO only comes out so frequently? So maybe we have an unspecified target for our spacecraft. We go and we say, we want to build a spacecraft with these characteristics that's going to go and visit a target like this, but I can't tell you the exact one. We can only say it's going to be like this. And we also need that dedicated launch vehicle, which we said was a challenge for those smaller spacecraft. Maybe we also have, if we think about that build after detection paradigm, long lead items become a real challenge. How do we build an entire spacecraft within 18 months if it takes me 15 months to get a solar array or a radio? How do we, again, those things are a little bit in tension. So perhaps we have these pool of parts where we can build some things prior to detection, store some things on the ground, but then build the rest of it, those bespoke items, or strap on our payloads later in time. On the engineering side, I guess I already touched on this a little bit, is some of those long lead procurement items. And also each mission is mostly redesigned from scratch, not entirely, especially I think as we progress forward, we're really leveraging, at NASA, I think we're really leveraging commercial industry and more standard offerings and trying our best to fit within those constraints, but still there's a lot, we said about a decade to build a mission, and so much of that is in this design part, in this formulation part. So we think forward and think about maybe modular spacecraft, similar standard interfaces, standard software blocks. New space, meaning this emerging space industry, I think is getting us closer to this world. I think small sats are a great way to look at more modular spacecraft or more off-the-shelf components that we could rapidly integrate into a full package to launch. Multifunctional components would be nice. And then testing. Testing is also, how do we make sure it's going to work? How do we ensure the reliability when we're building something quickly and maybe we're using parts from different areas? And how do we make sure that we are able to test this sufficiently well? I'll also touch on testing for a moment. I like to think about ground storage and test campaigns with ground storage. How do we make sure that we store something on the ground for a long time and we're going to have to define some test campaign that goes from getting it out and taking out of our vacuum seal in order to actually make it ready for launch, and what activities we have to perform so we can minimize that that testing period and yet still be as, yeah, we want to be safe, we want to be fast. So how do we negotiate those two things? And from a technology perspective, navigation is hard. I'm really happy that we have some experts in navigation in the room today and throughout this week, so we can address this challenge. We talked about navigating to dim objects, those small asteroid-like ISOs. How would we actually go and successfully navigate or maybe even impact something like Oumuamua? Small sats, you hear me talk about small sats a lot too. I think small sats are a great way to enable this kind of mission, but small sats have inherent limitations too. I think one of the biggest things is propulsion. So what technologies can we identify this week or going forward that we could mature that might be able to enable this kind of capability? Multi-spacecraft I think there's two classes, a homogeneous and a heterogeneous multi-spacecraft. If you have identical multi-spacecraft, maybe we have block redundancy. That's what we sought to achieve with the Xenia concept. Or with the heterogeneous, maybe we have more distributed science, or we have multi-agent science, which is really exciting. Autonomy might be enabling or might be enhancing. Autonomy can be extraordinary on the science side, that we might have limited bandwidth to downlink our data. So how could we select the best data that we possibly can in order to maximize our resources, our downlink resources? Or navigation, how can we employ autonomous navigation to encounter an object that's maybe 50 or 60 or 100 kilometers per second of relative velocity? I think the fastest flyby, Aircoth was pretty fast. I know that when we flew by Halley's Comet with Giotto, that was like 30 kilometers per second. I think that was the highest, but we also had an impact, and Giotto went into this uncontrolled spin and so recovered some extraordinary science. But how do we negotiate all these things? How do we ensure that we're safe, that we can encounter objects that are outside of what we normally will encounter in small bodies flybys, and still maximize our science return? So we made a couple recommendations to mature this multi-spacecraft architecture and maturing autonomy for technology, autonomy, navigation. I'm not 100% sure what Kimmy meant by manufacturing, but maybe it's what we're talking about, making things faster, long lead procurements, things of that nature. So looking out towards the future, we heard about the Decadal survey from Carol, but we wrote several white papers, and we got this great recommendation that I'll highlight again because I think it's so extraordinary. that in the coming decade, this is mainly for planetary defense, but I think there's so much synergy between rapid response for planetary defense and for the ISO LPC science to actually go out and do this after NEO Surveyor. And another thing I'm very happy about this recommendation is it actually gives us a time span. We always talk about like what is rapid response, how fast we have to go. So I'm very thankful to the Decadal survey for just giving us a number, less than 3 years. Like that's a great charter, and I think that's consistent with what we've seen before. And hopefully through our modeling efforts, we'll be able to go and continue to understand how frequently that happens. And when we talk about what determines the accessibility of a target, what determines the feasibility, now we can go and we can negotiate how many targets we think we will observe within 3 years and how fast we think we can go, and kind of say, we think we'll be able to encounter X% of ISOs that meet some characteristics. I think that's a really exciting modeling objective that we can think towards the future. We also recommended an increase in cost cap, as many others did. I don't want to say that we're solely responsible for any of these recommendations, but I'd like to think that we're part of a whole cadre that pushed some of these ideas forward. And we're excited to see an increase in that simplex small set cost cap, as well as increased investment in autonomy. So as we look forward, if we want to go and visit these NEOs, ISOs, or LPCs, which we do, they're such high value targets, we need rapid response in one way or another. I put forward 3 different architectures that have different flavors that we might use to achieve this rapid response. And we know that there are mission concepts across a variety of sizes or costs, from small sats to really big, exciting missions that might have multiple elements, like an impactor. Comet Interceptor has 2 CubeSats going along with it, which I think is great. But programmatic constraints are hard. I don't think we can overlook them. I think that's maybe even one of the harder areas in rapid response is the programmatic side. But through a coordinated effort by the science community, by the engineering community, and the technology community, I think we can make this a reality, and that we can achieve we can have no more missed opportunities in the future. So thank you, and I'm happy to answer any questions.